Okay, thanks. Good morning, everyone. I'm Iacopo Tirelli, and the work I'm going about is talking about my data-driven enhancement of optical measurement techniques. So, when we investigate on turbulent phenomena, like for example this one in the animation, surely the most challenging part is related to the wide range of turbulent length scale that are involved. And this kind of length scale are related to the Reynolds number that we are investigating. So nowadays, the most powerful technique, surely to extract quantitative information from this kind of flow, is particle image velocimetry or PIV. How it works? Imagine that this is our flow. No. Imagine that this is our flow, so we are seeding the flow with particles in order to trace the movement of the flow, and the objective is we use two consecutive laser sheets that sample the flow, and in the meanwhile, one or more camera are capturing what happened in the flow, so two instantaneous snapshots. The objective is to compute the displacement and consequently also the velocity vector of the particles. The domain is split in several interrogation windows, like the one that you can see in the picture here, and the corresponding velocity vector is computed with cross correlation. In a certain way, what we are doing is a sort of average, and we are smoothing the velocity vector that we are computing. So as you can imagine, the dimension of the interrogation windows is setting a sort of lower limit in terms of length scale that we are able to correctly capture. This is the classical PIV setup. Imagine that we want to focus on this part of the domain. So what our camera are capturing is something like this. So if we're zooming in, we can clearly see the two main limitations in terms of length scale that we are able to measure. The first one is the minimum length scale that we can measure, that is related to the minimum of the minimum particle spacing, while the second one is related to the size of the region that we are looking for. So we can define a ratio between them that is called dynamic spatial range, and our objective is to increase this ratio, extend this ratio. In particular, extending this ratio means extending our capability of investigating different Reynolds numbers, so different length scales. In particular, the objective of this work is to improve the PFV spatial resolution, pushing on the denominator of this ratio, so increasing the minimum particle spacing that we are able to measure. So now, with the objective of the resolution enhancement in PFV, I'm going very quickly show you all the activities and research lines that I carried out during my PhD, just a quick overview of them. And starting with the first work that we developed, that was the KNNPTV, that is a data-driven algorithm that is able to compute high-resolution flow fields starting from vector distribution, exploiting local similarity among snapshots, and trying with uncertainty embedded inside the estimation. On the same line, there is a technical note that we publish that is about correction on the mean flow based on ensemble statistics. So we are trying to correct the mean flow using ensemble statistics in order to avoid the modulation error that you have when you bring your data, vector data on annular grids. And this was more or less the work of the first and second year. At the end of the second, beginning of third year, I went to Brussels for a research stay hosted by Professor Miguel Mendez at Von Karman Institute. And the objective of this collaboration was enforcing the radial basis function framework that they developed inside our code, our algorithm KNNPTV. To understand why we were so interested in mixing the two things, let me talk about, this is where we just explain a first application of this methodology. Let me talk about what is a radial basis function. Basically, a radial basis function is a mathematical function that allows you to approximate a function like this one, the blue one, and depends only from the distance from some specific points that are the collocation point, the green spots. And basically, we are doing this approximation with the radial basis function by definition, and we can choose whatever kind of basis. In this case, for example, I choose Gaussian radial basis function, but you can choose whatever you want. And the unknown of this kind of problem is the weights that we need to give to the basis in order to better approximate this quantity. So we need to minimize the difference among these two, and in the meanwhile satisfy also some physical constraints that we can enforce, like for example divergence free, no slip condition, and so on. So these are the application of the two methodology. Here you can clearly see how this, the enforcing radial basis function is improving the resolution, especially in the near wall region. And the main novelty, if compared to the previous one, is that now we have also an analytical representation of the flow fields that allow us to do other kind of activities. After this, when we were working on this, we were planning to do a fully meshless algorithm able starting from the vector to obtain high resolution flow fields. But we had the last constraint to the Eulerian grid, to the matrix 4. That was the PhD that we were using to extract the information from the flow. And from this, we start a parallel activity that is what we call the meshless PhD, that is a novel approach to extract the PhD modes from vectors. So what people are doing now, when you have a scattered distribution like this, is to interpolate them on an Eulerian grid, so you obtain the discrete version of this, and later reshape these vectors in a matrix where the row represents, for example, the different time instant, and the columns represent the different grid points fixed in time and space. And PhD is able to distillate from this matrix the spatial modes that are the coherent structure that made your flow, the singular values that in this context represent the energy associated to these modes, and the temporal modes that are telling the behavior in time of this structure. So what we want to avoid is this intermediate step. So we want to avoid to pass through the grid, and we want to skip from this directly to this. And the solution to do this is applying the radial basis function for each time instance in order to have an analytical approximation of function of your field for each time instance. And coming back to the original formulation of PhD, we know that the temporal correlation matrix can be computed as the inner product among the different time realization in space. So by definition of inner product, each element of K can be computed using this integral. What we were doing with matrix approximation is basically a discrete version of this. So these imply a loss of information of resolution. So now that we have also the analytical representation of the flow, we can directly plug inside this integral and compute directly the integral using quadrature method. Once the matrix is fulfilled, we can decompose it with the SVD and obtain again the temporal modes that this time are analytical, and later by projection compute also the spatial one. We also submit a patent for this application, and we continue work on these future activities. Another side activities that we start also this time, also this one related to PhD, is what we call patch PhD. The patch PhD is more related to the investigation on large scales, like for example the one that Professor Sciacchitano showed you in the last seminar. Because on this kind of application, what people are doing up to now is to use robotic PIV to collect patch of the domain that are moving in space and obviously in time, but you end up in the end with a puzzle or puzzling all the patches all together in order to have a mean behavior of the flow fields, but you don't have instantaneous information. The question that we were posing is how can I extract from this kind of situation a spatial pattern, like for example the PhD, spatial PhD modes? And the answer that we are trying to do in collaboration with the people of Deft is using patches that are high overlapped among them. This means, for example, if you look the cube here in the animation, we can refer the information provided by the patch to a global reference system where outside the domain of the patch we put zeros, and the information are confined in the part of the domain where we have the patches. So if the patches are sufficiently large and overlapped, when we compute the 2 points spatial correlation, we can decompose it and recover the big structure that are made our spatial modes, basically. The last work before the conclusion will be, as I was saying before, development of a fully meshless algorithm able that combine the radial basis function, KNPTV, and meshless PhD in order to obtain this final algorithm for resolution enhancement in BV. The three work that I show you will be presented in Lisbon in a few months. The plan for the future, as I was saying, is to finalize these three works. The measure SPD is the one that is almost ready to be submitted. The other two requires a bit of work. And later, of course, put them together and start to think about the defense of the PhD and some outcomes. And that's all from my side. Thank you.